All right, so now just from the definition, what is the delta of n squared? Delta of n squared can be shown to be, I think that formula was derived last, when we talked about the grand canonical ensemble, is this thing. So this should be 1 over square root of n, which in the limit where n goes to infinity goes to 0, which is the thermodynamic limit. Okay. Okay, so the other thing that we can do is that from the expression that we just derived for n, so if I now plug in the expression for z tilde, then we get n is equal to, what is z tilde? Z tilde is this thing. So if I take its log, I just have this thing inside popping out. So I have e to the power beta mu v divided by lambda cubed. Is that correct? Yeah. This is kBt. That cancels the factor of kBt, the beta, or kBt coming from here. And so this is our expression for n. So we can now invert this expression to express mu, which is the chemical potential. And the expression for the chemical potential is 1 over beta, or kBt, times log n lambda cubed divided by v. Okay. So now what is v by n, n by v lambda, sorry. So v by n is the average volume per gas molecule, right? Or per gas atom. So that means that for quantum effects to be suppressed, we need to have v over n to be much, much larger than lambda cube. Is lambda cube? Lambda is the wavelength associated, the de Broglie wavelength associated to the average particle with the average energy. So this is the classical regime, right? So in the classical regime, the argument in the log is less than 1. Right? So that means that the chemical potential is a negative number. Okay, so we actually have a definite value sign for the chemical potential in the classical regime. Okay? In the quantum regime, it can have positive value, but in the classical regime, that's the case. Now, remember, when we introduced the chemical potential, we defined it as the amount of energy that we needed to supply per unit if we added a particle. So, so is this consistent? Is this definition consistent with the fact that the chemical potential is actually negative? Well, to see this, what we have to note about the definition of the chemical potential is that it's defined at constant entropy. So if we were just adding a gas molecule without changing the entropy, then what we would do is that without keeping the entropy constant, then we would add more ways of, increasing configurations. And therefore, we would be adding we would be increasing the entropy when we add particles. But if we are constrained to keep the entropy constant while adding particles, what we have to do is that we have to lower the energy. And that's why the entropy, that's why the chemical potential is negative. So that's what this equation means, okay? Because we have to keep S constant. All right?